There is only one aspect of autoregressive models that I would like to remind you of, which is remember that in the case of AR, the way you check stationarity is not really by working out the formulas, the second moments, and inspecting the fact that they do not depend on time, which is the definition of weak stationarity. But the way you do it is by going through the roots of the characteristic equation, which is essentially this polynomial in the leg operator that you see on the top of the slide, equated to 0 and solved. As with all equations, in math you were given equations just for the fun of it, just as an exercise. But the idea is that you need to solve them. So to find values of the unknown variable that satisfy the equation, and here you basically do the same. And the rule was simple. Once you have found the roots, there are p roots of the characteristic equation, you need to compute their modulus, which is the absolute value for real numbers, but is something more, say, for complex numbers. But this modulus, which is anyway a number, one single number, must be greater than 1. If it exceeds 1, then you have indications of stability, and if not, then you are in trouble because the model, let's call it, is unstable. Now, today we are going to use the same properties, so I wanted to review that in advance before I invoke that again with reference to ARMA models. Okay, so ARMA models, they are a few slides forward. Okay, here we go. And so let me use the whiteboard. So, not so good. Let's put it here. ARMA PQ model. So in this case, there are two parameters that indicate what the structure of the model is like. So P is the number of legs of Y appearing on the right-hand side. And Q is the number of legs of epsilon, of the shocks, appearing on the right-hand side. In a moment, you will see that. Now, let me start with a note. A ARP model is just a ARMA model in which you got P legs of Y and 0 legs of Q. So it's a special case of ARMA. And a MAQ model, the limit is down there, is just equal to an ARMA model in which you've got 0 legs of Y on the right-hand side and Q legs of the shocks. So you can see everything that we have done so far as a special case of ARMA. But although you should not be surprised to see something like these, so these special cases popping up in your software, the truth is that there are special properties of AR and MA that it is useful to know separately from ARMA, okay? Now, I say it is very mysterious, I understand, but in a moment, when I will do some pictures on the whiteboard, you will see what I'm thinking about. So what is ARMA model is when YT, whatever it is, but we especially care for returns, sometimes prices, but better is returns or interest rates, is equal to a constant that I call phi naught. And the fact that it has a name, whatever it is the name, tells you that it will not be identical to the unconditional mean. So there will be a formula for the unconditional mean, plus the sum. I never remember whether it's I or J. Good morning, Professor Reck is on the slides. Ah, you're right. Yes. I really like the kind way in which you, what are you doing? Share camera. Thanks, guys. I didn't write very much so far, but just a note. Right, I was actually checking, and it's very useful to do that for the people here, whether the index of the first sum is I or J. I never remember. It doesn't matter, obviously, but let's do it identical, so I. So the sum between I and P of the coefficients phi times y t minus I. So this is the AR part, okay? Now, it's a matter of taste whether you want to include phi naught in the AR or not. It's just the constant of the model. We just happen to call it phi, but you can call it Giacomo, I don't know, Marco if you want, okay? It doesn't matter how you call things. The important is that you know what they are. And in this case, it's an estimable parameter. Right, so I will put everything together, and this one is the AARP portion of the model. But it's not over here. There is also a moving average portion, which is the sum for j that goes between 1 and q of the theta j's times epsilon t minus j, plus you also put a shock. So a contemporaneous epsilon t shock. Remember that in principle, when you see epsilon t, there is like a phantom coefficient in front of it that is there, but you cannot see because it's just equal to a 1. And this corresponds to a typical normalization of the process, because otherwise you can rotate it. What does it mean to rotate? That if you multiply or divide all the coefficients, everything you see, by a number, you're changing, possibly you're changing the mean, okay? You're changing the variance, but you're not changing the memory structure of the process. You're not changing the autocovariances, okay? So by fixing one coefficient to a number, so we just use 1 because it's a focal number, then we are kind of pinning down all the coefficients and preventing them from being multiplied or divided without changing things. Okay, obviously this one, and here also it's a bit a matter of taste, so I will include epsilon t inside the moving average, but some people will not, so it doesn't matter practically. This one is the moving average Q portion of the model. Some people say, well, this epsilon t is actually the shock to both the ARP and the MAQ, so it needs to have a separate role. Okay, fine. It's not wrong, okay, it's just a choice. It's a philosophical thing. Now, one thing that is useful to do is to actually move everything that multiplies yt on the left-hand side, so just to be collected together, and to leave on the right-hand side all the things which are either not multiplying anything, okay, or they are actually multiplying shocks, so they are involving shocks. So if you do that in an expanded way, I think that for clarity once is good to see. So the left-hand side has 1, because there is yt, and then there is phi1 times L, where L is the lag operator, minus phi2 times L power 2. It's not a square, really. It's just the L operator applied twice. But it looks like a square. And actually, we kind of treat it as a square, kind of. Minus phi3 L to the power 3 minus dot, 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 phi p L to the power p. Everything multiplies yt. OK, so I just took this chunk here, the legs of y, and I moved them from the right to the left. And then I expanded them. And I collected yt. And there is yt after the parentheses, because every time I apply a certain number of times the leg operator to yt, these will get legs, which are the same things that you see up here. Okay, on the right-hand side, what do I place? Well, there is phi naught, poor guy, alone. Nobody wants it. It's just a constant. You can drop it. So the first thing that software does, and you may want to do if you do things by hand, is to take the data and subtract the mean. Okay, so if you do that, they have 0 mean, and so phi naught will go away automatically. Okay, and now I will write in expanded form everything else that is left on the right-hand side. So I have a big parenthesis here in which there is 1, this coefficient, plus theta 1 times L to the power 1. Why? Because it comes from here. It's theta j when j is equal to 1, multiplying a leg of epsilon, 1 leg, and the leg is produced by applying the operator L. Plus theta 2, L to the power 2, by symmetry. Let me also do the third, L to the power 3 here, dot, dot, dot. And then I've got the theta q, L to the power q. Everything is collecting together, and it multiplies epsilon t. Okay. Now, really, nothing has changed. I just moved one sum of legs of y from the right-hand side to the left-hand side, but it's important because that's the way in which we saw autoregressive processes being characterized by the characteristic equation when we spoke last week about autoregressive processes. Indeed, this object, inside parentheses, is usually named phi of L. Now, this is read function of L. So phi is a collection of terms, polynomial terms, which depend on the leg operator. Some people, some textbooks, they want to be pretty about it, and they recognize that this one will be a vector, characterize a vector of coefficients, so they put a vector, so they both face it, say. And this one, as you know, is the characteristic polynomial. So it is the characteristic AR polynomial that we have encountered already. Polynomial. So there are no differences compared to what we have seen already before. Now here there is a reason to write on top instead of the bottom, because I want to actually have information flowing down here and up here, okay? So this entire quantity that you have here is another kind of polynomial, obviously. It's another polynomial in L with different coefficients. The coefficients are now thetas and not phis, but it has a similar structure. Notice that the order of this polynomial is P, the order of this polynomial is Q. P and Q can be very different, okay? One is small and the other is huge and vice versa, fine. So this one is a theta of L that is to be considered as a polynomial function of L with coefficients theta. Again, is a vector. Some books actually, they put P down here to remind themselves that the order is P, and they put Q up here to remind themselves that the order is Q, but you do not have to. And this one is a characteristic MA polynomial. Now the question is, well, we understood from AR models that the characteristic polynomial is important because it drives the properties, the statistical properties of the process. So you will wonder, what is the theta Q of L is doing for us? Okay, so you will see in a moment. Okay, here I will proceed in black again, because this is very important. You know that if you set phi PL equal to 0, 0 is just a number, okay, it's a scalar 0, number 0, and you solve, so I put here and solve, the solution of this equation, polynomial equation, gives p roots. P roots. The roots are the solutions, very simple. Now, if, so there is a if condition here, the absolute value, the module to be precise, so I write in words, if the module of all the p roots is less than 1, is above 1, you will see soon, but in a few weeks, why sometimes there is a less sneaking in, is greater than 1, important, greater than 1, then you know that you have stability. And under some conditions, so here I will actually dash the other error. So in our case, surely goes from stability to the other property. Under some conditions, the two properties are equivalent. And I will write that in red, just for less emphasis. The condition which makes stability and the next property equivalent is linearity. But it's not so vital for us to invoke this property. Under linearity, stability is equivalent to weak stationarity. And some of you are thinking, however, if there is equivalence and there is linearity, we know that weak stationarity and strong stationarity, they collapse to be the same. So we're talking about the same thing. Weak stationarity, sorry, stationarity. Okay. Now, this is what I told you just when I started. So we study autoregressive processes through the characteristic equation, which is this guy here. So when you take the characteristic polynomial and you equate equal to 0 to find the roots, to check whether the module of the roots is above 1, because if it is above 1, then you have stability. If you have stability, you have weak stationarity. And in our case, for ARMA models, actually, you can also go in the other direction, true. And also here, there is something you can dash if you really want. But so all these things which are written at the end, they are equivalent. Okay, so that's fine. So what happens up here? So why do we care for the characteristic moving average polynomial? We care less compared to the characteristic AR polynomial first, because as you can see, the Phi polynomial from the ARMA model is giving you stability and weak stationarity, which we really care for a lot, because remember that from weak stationarity, I still have some space, which is magic. There is the chance to produce forecast. This is why we care for weak stationarity, because it means that the time series may have memory, but this memory fades gradually. And so the time series is forced to go back through the unconditional mean. So if you see a very high value today compared to the unconditional mean, you know that eventually the time series will have to go back there. And so this allows it to forecast. So if you see very high values, you expect them to decline. If today the values of the time series are very low, below the unconditional mean, you know that eventually we'll go back up there. And so you expect the series gradually. You don't know how fast, you don't know when exactly, but you expect the time series to go up. And that is forecasting power, and these are in finance trading strategies. Okay, what happens up here? Now I'm changing color because I want to, for emphasis, fine, but also because I want to give less emphasis. So blue is less visible on purpose. So by studying the characteristic polynomial, you can do something similar. So let me go this way. So if you take theta QL and you set equal to 0 and you study the roots, also in this case you will find Q roots. So same things, you use the same machinery inside your computer, so there is no difference. If the module of all Q roots is above 1, okay, then there is a property which ensues, which follows, which is called invertibility, which I will write here, invertibility. We say that the ARMA model, because of properties of its May component, is invertible. Okay. What is invertibility? Now, let me add, so still I go back to black down here. Well, you know that there is a bonus from weak stationarity. Weak stationarity allows you to forecast, but actually it allows you to do something else. If you have weak stationarity, then you can invoke the Wahl's theorem. Wahl's theorem. And what does the theorem says is that the Wahl's theorem is equivalent to, so I put a double arrow because that's the statement of the theorem, that YT, so the autoregressive process, so ARP, is equivalent, is isomorphic to a moving average infinity. Okay? And that was the important thing. So even if you see an autoregressive process, this process may be written as a moving average infinity. Now, it looks like a curiosity today, but it speaks about two things. If some conditions are in place, then being able to write an autoregressive as a moving average infinity directly in red speaks of linearity. So you know that being written as a moving average is not equivalent to being linear, but it's one step from there. There are just some conditions that need to be satisfied, but you're kind of there. Second, you will see that in the future, it means that some types of calculations, which are easily done using moving average models, they can be applied directly to autoregressive processes, first by rewriting them and then by exploiting those calculations. Now, today, it doesn't yet make sense, so I just write it in red, but with a question mark here. They will be called impulse responses. Impulse responses. Don't worry, never explain what they are, but when you go back in the future, in May, to study, these will make a lot of sense. Yeah. Okay. Now, we got something similar here. So basically, in the end, they will be nearby. I'm just moving epsilon t a bit because it is in the way, but just a bit. Okay, under invertibility, then you have a similar property. You have equivalence. So you can write something as something else. You have equivalence between MAQ and AR infinity. Now, this property, so the fact that instead of manipulating a moving average, you can manipulate an autoregressive process of infinite order, is less interesting than the property in red, than the Walls theorem. And indeed, it does not have a name, so it's not a theorem, it's not a celebrated theorem. When does it matter? It will matter to us today in 10 minutes, 15 minutes, when we talk about the partial autocorrelation function of moving average processes. All right, so it helps us in that bit. And second, it is very useful if you are into proofs, mathematical proofs, because some things that you want to say about the moving average process, they are easily said, they are easier to do and say when you go through this type of representation. So here, for our purposes, I will write here in red, Pacf. Partial autocorrelation function, because I'm going to use this property in a second. All right. So under some conditions, this apparent distinction between AR and MA falls. But there is one catch. You can represent AR as MA, or you can represent MA as AR, fine. But when you invoke the representation, there is an infinite number of legs which pops up. Okay, so to carry around an infinite number of legs, in theory, it's okay, in a textbook is okay. But in practice, when you are in Excel, you cannot have an infinite number of legs because it's more than the number of observations you have. So these equivalencies, 1 and 2, they're useful in theory, but they're not useful in practice. Okay, so that's the theoretical side of things. All right, what is the practice? Well, this is practice. This is what we are here for. So that's what you want to do. And it doesn't go through the Walls theorem. So before you get lost in, so that's a way to review AR and MA processes, but once I give you a ARMA process, you got both together. So you can study the AR characteristic polynomial and get down and check whether there is stability and stationarity. You can study the roots of the characteristic MA polynomial and establish whether the ARMA model is invertible or not, which is less important, but you may want to do that. A machine software will do that automatically for you anyway, okay? So you will see a printout with this info about these roots and this info about these roots automatically at the bottom of the page. And so why am I speaking about this in class? Because if you see that printout, it must be meaningful to you. If there's somebody asks you, so what is that number? Where does it come from? It looks like a complex number. What is that? You have to be able to say, oh yeah, don't worry, it's just an invertible process, but probably will not matter to you in practice, but I don't know. Okay. So the question is, but when I give you ARMA, you got both things, both stories going on at the same time. So which is the important story? Well, I say that if you're here to forecast and not to do theoretical proofs, we care for the black story at the bottom. So we care for stationarity, we care for stability, we care for the P roots of the ARP characteristic polynomial. So it's the autoregressive part which wins. And you will see also in the case of ACF, PACF, in what sense that is the case. Now, let me go back to slides through Blackboard. So I need to share files. Okay. So let's see the slides quickly, but they say, hopefully, the same things which I've said. Right, there is an Excel file, so the famous Excel file, which we already played with a couple of times, optional, also has a worksheet, a page for ARMA, but it's just ARMA 1.1. So you can play with that, right? So you will see some of the things that I'm about to speak about shaping up in front of your eyes, but there are two problems. It's just 1.1. So it would be useful to have a 2.2, but it was too much work. And second, as you saw, some of you already actually picked it up, there is only the ACF, because to compute manually the PACF in Excel is a bit of a headache, because you have to run a number of regressions and pick out the right coefficient. You can do it, okay, but pain. And so I prefer to show you these type of things, so ARMA models in the lab when Evius does the calculations, because I mean, it's just, with one click it does everything that Excel does in hours. All right, so the definition is here. The rewriting of the model is here. So here I'm telling you that the dominant portion of the ARMA model is represented by the AR part, because the AR part is in charge of driving stationarity, stability, and forecasting power. Because there is an AR component in play, the same things that we said about moments in the case of AR apply in this case. So I can show you one formula. It's very simple, because it is identical to the case of ARP. So the only moment for which there is a easy closed form expression is the unconditional mean. The expression is the same as the unconditional mean of an ARP model. Okay, so fine. So, and why? Well, from far away, you see that these guys, they are white noise with zero mean and constant variance. These guys, they cannot shift the mean up or down, so they do nothing to the mean. So having them in or not does not move the mean of the process. Do they move the variance and the autocovariances? Yes, they do. But they don't do that in very simple ways that you can easily trap in a formula, in the sense that also in the case of ARMA models, you can see the book if you want to see some calculations, the way in which you characterize second moments, unconditional second moments, so the variances and the autocovariances, is by writing down and solving the Yule-Walker equations, which is a system of equations, right? So very quickly calculated in a computer, but painful if you have to do it with paper and pencil. So just, I don't know why, but just to show you how difficult things pop up, I showed you one result. So that's the ACF, the theoretical ACF of leg S, of order S, from ARMA PQ model. And as you can see, rho S is not a formula with the coefficients on the right-hand side, as you would expect, but is a recursive equation which relates rho S to rho S minus 1, rho S minus 2, dot, 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 rho S minus P, where P is the AR order of the process. And what is the meaning? That if I know rho 0, which is always equal to 1, then I can compute probably rho 1. If I know rho 1, I can compute rho 2. If I know rho 2, I can compute rho 3, and so on. So you start the recursion until you have all the numbers which needs to be plugged inside this one. But if you try with paper and pencil to work out, to write the formula in terms of phi and theta coefficients corresponding to what you see here, maybe you manage, okay, but it will be incredibly long. So it will take the entire whiteboard to write the formula. Okay, so people don't do it. I mean, it's just crazy. Okay. Now, so the other thing I want to do, why do you do this? So the thing that you see at the bottom is actually not supposed to be like that. If you look at the poster slides, there is a table. And I don't know why it keeps actually printing the wrong thing. So let me show you the table here. So this table should also be printed at the bottom of that slide, okay? I have it correct, but it's not worthwhile to upload it. Now, I want to do this table with you on the whiteboard with pictures instead of just words, for memory, essentially. And so the point is, what do the ACF and the PACF of the ARMA model look like? Well, the beauty of ARMA models is that the ACF and the PACF, they look the same. Better, let's qualify. After Q legs, the ACF looks like the typical ACF of an AR model. That's not surprising, because I told you that the R1 is the ARP is the winning component of the model. So it takes over. And after Q legs, so after this guy is exhausted, there is only autoregressive happening for you. The PACF of an ARMA model looks like the ACF of the ARMA, so it behaves in the same way, which is it declines towards 0 either geometrically or in an oscillatory fashion, but this happens only after P legs. So essentially, once you take away the PACF inference of the autoregressive process, you have the MA left, and it behaves like the typical PACF of an MA. What is the PACF of an MA? It goes down to 0 gradually. Now, let me show you in a picture. So this is identical to what you have in the page, but I think this is more visible. So I want to speak of ACF here and PACF here. These ACF and PACF are the theoretical ones, the ones you should obtain from the process or the one that you can compute if you simulate lots of observations, 1 million, 10 million, things like that, okay? Now, it's not, I mean, if you are in Python or MATLAB, I think you can afford 1 million simulations, so I mean, it takes a bit, but it will do it, but not in Excel. Okay. So let me start reviewing the old things. So here I want to place ARP. Let's make it a stationary ARP, weekly stationary. Okay, so a good ARP model, one that allows us to forecast. All right, so what is the ACF for an ARP model like? As you know, there are two cases. So one case is, so no hat on top of the row because it's the population one. So one case is when the ACF declines geometrically, so something like this. Ah, right, yes, I know. Agostino, you're very good. I don't know if it was Agostino also before, but I love the way, good morning. No, this is perfect. No, actually, it was Alberto, Nicolò. So you all coordinated in saying good morning when you're saying the professor, you fool. Would you? I'm admired. Bravi, bravi. Sorry, I'm lost. Thank you. But I didn't realize it's cutting a bit here. All right, so here there is weekly stationary, guys, but I will move ARP. Yes, at least now it's visible. Right, I was saying that these the first type of shape you get from ACFs is that they decline slowly geometrically towards 0 from above, okay? Now, they can do that in many different ways, in a very convex way, in a more linear way, but more or less they go down towards 0. We saw a few cases before. This one looks like the typical AR2. But there is a second type of shape, and this one I will do it a bit funky. -1, +1. Funky because I will do something which has a period of 3. And it's a funny period. So it goes like this. And then, well, it's going down a bit slowly, too slowly probably. Okay, better this way. And then, let's do like this. And then like this. And then like this. Okay, so you see what's happening. The period is 3 because basically it's repeated every 3 legs. And it turns off gradually towards 0, but it oscillates. All right. So we never saw a period 3 one, I think, but we were able to produce a period 2 ACF in Excel playing with the coefficients. So if you play, you will get things that look like this. All right. So this has been seen already. What about the PACF of an ARP process? Well, the property of the PACF, see also I can do that for the class. See also the table, is that the PACF of an ARP process cuts off after P legs. So there is only one possible shape, and I will do one that This one is probably corresponding to this one, okay, but we don't know, it's just a qualitative picture, so boo. Okay. Right. So the first two, the first in general P are alive, so the PACF is non-zero, it's statistically significant, say what you want, and then it dies. It's identically equal to 0. And the number of bins that you have alive, non-zero, gives you indication for the value of P. So the number here, so this guy here, in principle is equal to P. Okay. Now, the bins, they can stick out in all directions. They could be both negative, both positive, right? Because the bins, so these values here, they're a function of the roots of the process. They are not really just a function of the coefficients. Now, to have a negative bin, you need to have at least one negative coefficient inside the ARP, more or less. I cannot see special cases of that. But the relationship between coefficients and the PACF is not a trivial one. All right. Okay. Second, the moving average process. So MAQ. Now, I want to be able to look at the PACF of the process. For that to be the case, I need to be able to represent my MA as an AR. When can you represent an MA as an AR? When you're guaranteed to be able to do that, when the process is invertible, which has to do with the roots of the characteristic polynomial of the MA, not of the AR, which is the thing that you have in blue up there. So before drawing the pictures, let me make the assumption that the MA is invertible. Now, I do not write anything about stationarity. Why? MA processes, by construction, they're always stationary. They are weighted sums of white noise, so they have to. Okay, what is the ACF of an MAQ process like? Well, it has the same properties of the PACF of an AR process. So it is what it is, but then suddenly it stops, it dies, and it never comes back. So in picture, the ACF of a MAQ can be pretty funky. We will just write one because qualitatively it's just one that you need. So it can actually do funny things. So I don't know, like negative and bigger, then big and positive, then small, I don't know, things like this. But then suddenly it dies. And from now on, it's always equal to 0. Cuts off, that's the word. So the last bin, which is non-zero, significant, say, gives indication for the order Q of the MA process. So this one, in principle, corresponds to Q, the order of the process. Now, notice that there is correspondence between the qualitative nature of the PACF for an AR and the qualitative nature of the ACF for a moving average process. They are not identical, so some of you guys may want to actually not do my drawing, or actually on the side of my drawing, copy exactly this one, because, I mean, they could be the same. They're different processes. So, okay. Now, in this case, there is, this picture is pretty simple. This one is pretty funky because this Q is much bigger than this P, but whatever. Okay. What about the PACF? Well, because under invertibility, a moving average process can be written as an AR process. It means that it can be written as an infinite autoregression with infinite coefficients, right? So all these coefficients, in principle, they could be different from 0. But remember, what is remember, what is the PACF? The PACF is a mechanism through which you estimate a regression, and you pick the last coefficient out of the regression, and you save it and plot it. In this case, how many regressions, in the case of MA, how many regressions can we estimate, pick the coefficient, save it, and plot it? Well, infinite. Why? Because under invertibility, it is up here, a moving average process may be represented as an AR infinity. Therefore, because of this, the PACF of MA is something that decays towards zero, either geometrically, slowly, or in oscillatory fashion. So the PACF properties of MA are identical to the ACF properties of ARP. So they are like inverted, okay? So the cross moves in this direction. And in principle, you can copy both pictures that you have up there. So quickly, H, rho H, plus 1, minus 1. So there is one, I don't know, going like this. So now I will do something that decays slowly, but there is nothing special or wrong with that. And then I will do a classical oscillatory one. And well, very classical, okay? So bum, 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 bum. So it decays pretty fast in my picture, but in principle, it keeps going forever. It keeps oscillating forever until it's infinity, until it reaches infinity. Okay. So if you encounter a PACF and the PACF never dies, probably you're looking at the moving average process. If you encounter a PACF and the PACF suddenly stops, probably you're facing an autoregressive process. But there is still one issue. Is the PACF so final? No, because the PACF, you will see that in a second, cannot discriminate between ARMA and MA. It can tell you whether it is something AR, so here it's different from here, right? But unfortunately, you will see that the same pictures that I've got here, they will copy it below for ARMA. So the PACF is not resolutive when it comes to distinguish between ARMA and MA. So let me do the third case. And the words, unfortunately, they are in gray, but I think you can see them. I only have them in gray. But at home, you can see the right table at the right slide, which is the slide that comes later. So this one is ARMA, PQ. And in this case, it's worthwhile to say that it's both stationary and invertible. So stationary and invertible. It's not a waste of time to say weakly stationary almost. Okay, so W stationary, fine. So now for ARMA, the ACF and the PACF, they behave identically. So they both go to zero. They can do that gradually in a geometric fashion or in an oscillatory fashion, but they go towards zero. So first case is, I will just draw the geometric case just to save space. So plus 1, minus 1, that's rho H. So let's do it geometric. But, okay, before I do it, I know it's in gray, guys at home. I don't know, these are my slides actually. Here in the classroom, also here, look at this. Okay, we have it the right one. So notice there is one detail, which is ARMA PQ decays towards zero, the ACF starting at leg Q, and it decays towards zero, the PACF starting at leg P. So when you do the picture, there is going to be a difference between what happens after Q, say here, that's Q, and what happens after P in the case of the PACF. So here, same picture, H, this one, sorry, I did something silly. The way we called the PACF is not rho, obviously, it was phi. So these guys here, they should be phi. All right, and I can do this right. It doesn't matter how you call them. So it's not rho, it's a phi, it's a guy like this, okay? It doesn't matter how you call them, but it's just a different symbol from rho. So plus 1, minus 1, d. All right. So in this case, what matters is Q. So things are going to change after a number of legs called Q. So what the table says and what you can prove is that the ACF dies towards 0 gradually after Q. Before Q, it can do whatever it wants. So let's actually split them. So I don't know, here I will do something like this. Okay, so you see what is happening. What is wrong? It should be P and not, yes, this guy here should be, grazie, thank you. This guy here should be P, apologies. So it dies after P legs. So after Q, we know what is happening in the sense that it declines towards 0. You can do an equivalent picture in which it goes in an oscillatory fashion. It's just a matter of taste, meaning it will depend on the roots of the process. So, okay. Before Q, here, you can actually go crazy, Cirque du Soleil. So I don't know, I will do a crazy one, like look at this one. I don't know how likely this is, all right? I'll do a positive one because I don't think otherwise. Why not? Why not? So it means that in this stage, the MA coefficients are so big and negative that they swamp the autoregressive coefficients and they impart this negative characterization to the first 3 legs of the ACF. Why not? Now I told you, so I mean, from far away, it looks like 2 things are happening. It seems to go towards 0 from below, which I told you in the ACF of an AR, it's impossible. But why is this happening? Because it's the MA working and giving this. And it seems to cross. What did I tell you about ACFs? Either they oscillate or they go down towards 0. They are not crossing, okay? So going from positive to negative and vice versa. But here you have the impression of a crossing. It's a fake impression, meaning it's the moving average coefficients at work because they are more important compared to the autoregressive ones. But after Q legs, the moving average coefficients, they're off because the epsilon memory of the process is completely lost. And what is left is only the roots of the autoregressive process, and the roots, they do exactly what you see here, or they oscillate. But you know what will happen. They will go to 0. Okay. So from far away, I basically kind of drew the tent of the Cirque du Soleil here. Not on purpose, but. So when you see very funky ACFs, they seem to go all the places, but then eventually they kind of become regular and they go towards 0, or they start oscillating towards 0. That's ARMA speaking to you. And the funky things that happen at the beginning, they are due to the coefficients, the thetas of the moving average part. Okay, same here. So you know what happens after P. It must go to 0. And in this case, let's do a picture in which it goes to 0 in an oscillatory fashion. So, boop, 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 boop. Okay, it goes like that, fine. And this will happen when the roots of the moving average polynomial, some of the roots are complex. So this is what responsible for the oscillations inside the phi h, the PACF function. What happens before? Whatever. Cirque du Soleil. So I don't know. So big, big identical, then negative, negative identical. This is pretty funny, right? So there is no trend, it's just positive and then negative and then boom, and then it declines. But why not? So the point is anything can happen here because that is driven by the MA coefficients and the AR coefficients, with the AR coefficients very active here. Okay. So what's the problem? I mean, the PACF is not restorative because it declines towards 0 here and also here. So if you look at it from far away, you will not be able to say whether it's ARMA or just MA. You know that there is MA involved, but you don't know whether there is also AR or not. But every time you see a PACF doing this, so boom, suddenly stopping, so this AR, then you know that it's an AR. Same thing for the ACF, in the sense that there are 2 reasons for why the ACF may decay towards 0. First is because you're facing an AR process, okay? Second, because you're facing an ARMA process and you don't know. But if you think about it, joining the knowledge of ACF and PACF, you will know. So just one column is not enough to actually tell you to distinguish. I mean, it does not allow you to distinguish all the three cases, just 2 against 1. Also here, but the 2 against 1 of the 2 columns are different, and so if you use the overlapping information, you're able to, in principle, you're able to say. Okay, now in practice, is that so easy? Which leads me to the next question. So I will write it so that people also see me from home, and then I will switch back to slides. There is an example of ARMA in the slides I will show you in a moment, but as always, it's just an example. So the question is, and some of you already asked me this question, which is the natural one. Prof, but in reality, I will not simulate the data, right? So my boss will give me the data. Or I will download the data myself because I need to write a thesis, say, okay. So how do I know whether I'm facing AR, MA, ARMA? What is the order of the AR, the order of the MA? So what do I mean, how do I know? By looking at the data. Yeah, thanks. That's the big question. Knowing is very important because if you specify the wrong model for your data, so the data, sorry, the model the data do not come from, then your forecast will be of poor quality and it will show that you did a poor job. Time will tell, basically. Okay, so the question is, how do I specify P and Q in ARMA PQ? Why do I write the question in this way? Well, you know that if you specify either P or Q to be 0, then ARMA simplifies to be just AR or just MA. So talking about the specification of P and Q and talking about which kind of model is actually equivalent, is the same thing. What if both P and Q are equal to 0? Well, then your data are telling you that they are white noise. So they have no structure, no memory, and your ARMA collapses to be a white noise. So the first way to do that we spoke about already, is using sample ACF and sample PACF, compare them with the theory knowledge. It's really almost just getting data, computing the sample ACF and sample PACF, comparing the pictures that you get from your data with the whiteboard that you have on top. And hoping, you will see more examples in a moment, that the data tell the truth easily. You know, they don't behave like spoiled kids. Oh, I don't want to tell you, don't want to tell you. And sometimes they will do exactly like that. So that's why there is not only number 1, there is also number 2 and potentially other numbers in that list. Let me go to the slide. Slides. Yeah, we are fine. Rec is on the slides and you're slightly out of the picture on the left. Yes, I realized that. Okay, we are fine. Right. Thank you. I hadn't seen that. I realized by myself. Hello? So there is an attempt to give you one example of ACF and PACF of a normal model. Here. So if I just show you the data on the leftmost plot, I mean, I think it's visible, it's not a white noise, okay, fine. But whether it's AR, MA, or ARMA, it's a bit spiky, in fact, so this makes me think that there is some MA in play. But, you know, it's very easy to say these things after you simulate the data and you are in charge of actually choosing the process. So some people would just look at that and say, look, it's an autoregressive. I don't know whether it's an AR1, an AR2, an AR3, because it depends also on how big the coefficients are. But fine. And so on the right, there is, to the benefit of the people in the classroom, let's make it bigger. There is the estimated Acf and Pacf from this data, 1,000 observations. So the sample is not really huge, okay, just to say. And the Acf kind of declines smoothly, geometrically, I would say, towards 0. Geometrical in the sense that then it becomes negative after leg 11, but you know that there is a bias in sample Acf when you do not have many observations. So it's not a rule, but they do tend for high legs to produce these negative, small negative bins quite often. You noticed already in the past. But up to leg 9, 10, say, it's quite clear what's happening, geometric decay. So this tells you that there is for sure one type of autoregressive component. It's not clear whether, however, it's just AR or not, and the order of the AR. So you resort to the PACF. And here, the PACF with 1,000 observations and with these coefficients, 0.7 and minus 0.3, is not shockingly revealing. Because to some people, when they look at that, they will say, look, it's clear, right? After 2 things, 2 bins, there is nothing left. And when the PACF is of that type, you're looking at autoregressive process. After 2 bins, there is nothing left, so it would be autoregressive too. And most people, I think, would conclude that these data came from an AR2. That is the wrong conclusion, right? I generated myself the data. They are from ARMA 1.1. So that's a general difficulty. Many ARMA 1.1 models, they hide behind autoregressive 2, or vice versa. But usually people, they tend to prefer AR2 over ARMA 1.1 because it is simpler to deal with AR2 compared to ARMA 1.1. That's a general problem, okay? So many analyses, even famous that you see out there in the literature in econ or finance based on AR models, I think that the data, they liked equally a ARMA model, but it was easy to go for AR. Some people may be cautioned by my words. They will look at the PACF and they will say, well, it kind of disappears, but then I noticed that every 12 periods, it pops up again. See, 24, 11, 12. This bin at 11 is not really that small compared to number 2. So they will try to imagine, but it takes a lot of imagination, that the PACF is not definitely dead after 2 periods, so it keeps going. Say. And when the ACF keeps going, then you know that it could be in the last case, the ARMA case. You cannot be in the second, because in the second case, the PACF keeps going, but the ACF should stop, which doesn't happen, right? So the plot at the top is very clear. But so if the PACF keeps going with the type of ACF that we see there, then it must be an ARMA model. Now we know the truth. It's an ARMA model in which the MA component is kind of weak, because minus 0.3 is not a shockingly big coefficient. Right? Now, why did I do this example? Because I wanted to introduce what follows, in the sense that even though in principle we try to use anytime we can ACF and PACF to specify the ARMA model that we are going to use, often this is not enough, because we do not have enough data, or because the data, as I said, they tend to mimic the behavior of AR processes instead of revealing simply that they are ARMA processes, and vice versa. But I'm more worried for the first case. Okay. So let me show you a real-life example. That's monthly CPI inflation in the US. The data are from 2000 to 2016, so it's 16 times 12 observations, like 200 observations, a bit less. No, 16, yes, 16 times 12. So not a lot of data points, okay? And this matters because if you look at the confidence intervals in the picture, in the ACF and the PACF, they are quite big compared to the ones that we saw in the past. Because in the past, those plots were based on 1,000 observations, not less than 200, so it shows. Now, these contributes to problems in identifying where the model, where the data are from, so what kind of model has generated the data. Because some people, they approach these pictures and they look at the ACF and what they see is oscillation. The oscillation seems to get weaker, but very slowly, by the way. So it's oscillation, so it means that some of the roots are complex, but the module is actually pretty big. You will see what this means. Okay, now, if you are careful about the picture, however, there are some issues with the period, because it seems to have like 1 or 2 periods, so the period seems to be 2 positive bins. Then there are like 7 consecutive negative bins, and then 3, 4 positive bins, and then another 6 or 7 negative bins. So it seems to be 3 and 7, 3 and 7, which suggests that something quite complicated is going on in the background. But basically, we stop the movie in the bad place, in the sense it would be nice to see what happens in 25. Okay, I didn't want to do that because, you know, I mean, the reality is that you report the Acf and Pacf once you have decided, not before deciding. And it's always arbitrary. So essentially, you could stop the Acf, say, at 20 in this case, or at 16 without losing much. So the oscillation seems to be quite clear. What about the Pacf? So remember, if this were an autoregressive process, the Pacf must die. Does it die? Well, the first 2 bins are significant, and then there are a bunch of bins which are not, but the 8th is just at the edge, and especially the 24th is statistically significant. So is the 24th bin for the Pacf just due to luck, or is it there? And it's trying to tell us something. So this is the question about the analysis of this time series. So if you want to play smart, and you're not afraid that your boss is asking you to redo it and show more, you could cut these plots, just show the Pacf up to 20, say, and it will be fine. So that's an autoregressive process of order 2, right? But if you show everything, and then you have this bin at 24, then it's more trouble. And actually, what would be interesting to do is to go beyond 24 to see what happens next, right? So I didn't do that for visibility, right? But you have latitude in what you can do. But careful, if you start playing games with where you cut things, then it is possible that your boss asks, but show me up to 50. And then you will look like a fool if you were careless, so careful. If you don't think the Pacf died after 2 legs, so if you think that 24 is there, it's not luck, it's there, and maybe even 8 is there, then you're facing a case in which the Acf is oscillating, and also the Pacf seems to be weirdly oscillating. So they're both oscillating, and then you are in the ARMA case. Indeed, inflation is the typical series for which, since ever, people are debating whether you should use AR, just AR, or ARMA. Okay, ARMA seems to be the winner recently, but there is a period back in time in which they were just specifying AR models. Now you're like, well, is it so important? It depends on what you have to do. In some applications, no, because anyway, the data are what they are. So they are trying to express themselves either through AR or through ARMA. So they will try to tell you the same things. But if it comes to forecasting, to have an AR or ARMA will spit out different numbers. Okay. Now, inflation is a tradable series in the sense that there are derivatives written on inflation. And you know, if you are producing suboptimal forecasts, you will make less money than you could, or actually you will lose money because somebody else with a better model will exploit you. And that's a problem if you lose money. Right? Professor, why do we see 0 p-values even next to insignificant? And then he went away, but I think I understood. I think it was Anton. Anton, remember that, first of all, this prob refers only to the AC, not the PAC, okay? And also, this is the p-value, the Q-stat. The Q-stat has a cumulative nature. So, so for instance, if you read the 0 corresponding to 18, when there is not much, actually, let me pick 16. Okay, in correspondence to 16, the Acf is not significant, right? You guys see that. But the p-value is 0. Why? Because this wants to be a test of the first 16 legs in a cumulative fashion. And before 16, there is 1, 3, 4, 5, 6, 7, 8, 9, and then 11, 12. Okay, you see that, which are all significant. So this p-value will stay 0 up to 200, up to the end of the series, really. So it's a cumulative. Right, I was saying, okay. I was saying blah, 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 it's tradable. Okay, no, fine. All right. So in the rest of this lecture, which I should be finishing when? Like now? 10, okay, good. And then, okay. I mean, these weird times are a bit, okay. No, so I made up time compared to, oh, fine. So this motivates the rest of the lecture, which wants to be about how do you choose the best possible model, okay? So one way to choose is already on the whiteboard, is using Acf and Pacf. And I already showed you one simulated case and one real-life case in which we are in trouble. In the simulated case, the Acf and Pacf may lead us to say the wrong thing. And I know, okay, just 1,000 observations, why don't you simulate more? Maybe the coefficients were a bit tricky because one was minus 0.3. I understand, but reality is not there just to wait for you, right? Just to be simple. So, I mean, it's a good simulation actually to think about. Then we got to real life data, very important data that everybody's looking at, and it's not clear whether it's ARMA or AR, and it may matter. Okay. So we need maybe something more and better compared to just Acf and Pacf, which, however, I need to teach you, okay? So they are in the toolbox. The next thing that people nowadays are using probably more than Acf and Pacf is information criteria. What is an information criterion? It's a sample statistic, so it is a function of your data. And as a sample statistic is a random variable, remember. So if you draw a new data set, and from the same phenomenon, you draw a new data set and you compute the information criterion, you will get different values. And the nature, so their spirit, is to trade off, so to exchange goodness of fit for forecasting power. So information criteria are expressly informed after our objective, our goal, which is not just to fit the time series, but actually to be able to forecast the future behavior of the time series. And the idea is that you're considering models that can be sorted from simple models to complex models. In our case, what is the simplest model? White noise, when there is nothing to talk about. What is a complex model is when P and Q are large, because you allow lots of legs of y and lots of legs of epsilon to appear on the right-hand side. So the idea is, should I stick to low numbers for P and Q, or even zero numbers for P and Q, or allow them to be big numbers, so to have big ARMA models? Now, if you assess a complex model, what is the advantage? Being complex, the model fits the data better. And the language you are probably used to from econometrics 1 is that bigger models, they increase the R squared that you get. And it's natural, right? So the more stuff you put on the right-hand side, the better you will be able to track the data that you have. However, bigger models, they are cursed by one tendency, which is called overfitting. Meaning a big model with many parameters will use the parameters which are provided to the model to go in and fit every individual data point. So basically the model will be taken all places, just like pulled in all direction from individual data points. And this could be very bad in terms of forecasting, okay? So I need to do a picture for you and write something as well. And for the first time today, I will remember to switch view before you tell me. Share camera. All right. So this is number 2. Information criteria. Let me write here, trade-off, fit with parsimony. The fit is measured by, so let me do that in blue, by, well, the measure that it's natural to you, I think at this point, is R square. Careful with R square, we are looking at ARMA models. In ARMA model, the past of a series, the past of the very series, or the past of the shocks of the series, they are explaining the future. So is that true explaining, connecting the past of a series to the future of the series? To me, not. It's a very, sort of a tautology, right? So what happened in the past conditions the future, which is always true if you think about it almost most of the time. Now, when you encountered R-square is when you were looking at regressions. In a regression, some variables called regressors, explanatory variables, or independent variables, they are explaining some phenomenon called Y. That was intellectually challenging. I'm finding the forces X driving some phenomenon called Y. And the R-square was measuring, in some special sense, how much of the variation of Y was captured by the X. That is a good use of R-square. In our case, R-square, I mean, I'm explaining Y with the past of Y, so it's a very easy task. So I'm not saying that time series is not useful. I'm saying that the yardstick to measure time series performance is forecasting power, not explanatory power. So R-square. Now, in our case, what is best to think about is something which is behind the R-square. It's called the residual sum of squares. I think you saw that in econometrics 1. And it will be called sigma hat square epsilon. Okay, don't worry, because it appears in the slide, so I want to have it on the whiteboard as well. What is parsimony? Parsimony is simply measured by the number of parameters. So we will be called K equal to number of parameters. Notice that in the case of ARMA models, it's just P plus Q plus 1, because in ARMA models, you have ARMA PQ, right? The plus 1 comes from the fact that typically we specify an intercept called phi 0, something. Now, it's very weird, so you don't see that done, but in principle, you may dream of estimating ARMA models without the intercept. I never saw that. I don't know what's the meaning, but I know that Francesco Corelli loved the case without intercept, so in case you're wondering, it's never done, but okay. Why? Because the intercept is actually netting the mean out of the data. That's what it does. And you know, it's useful to have something that cleans the mean out. Okay. Now, why do we care for parsimony? Because, so I don't know how to do that now, but so here in black. The idea is that non-parsimonious models tend to overfit the data. And overfit is bad. Picture of overfitting. So that's an econometrics 1 picture, but I just want to give you the intuition. So you got Y and X, and you got data on these two variables. And the data, they are kind of, I mean, not badly behaved, something like this. So that's your typical cloud of points. So if I ask you to do a regression of Y on X, you are basically fitting to the data a straight line. And there are two parameters, the intercept, say alpha A, call it as you want, and the slope beta B, so call it as you want. So in this case, based on my picture, you will get more or less, I think, something like this, more or less, okay, just eyeballing. And it just happens to go through the origin, but you still have estimating the intercept. Alpha came out to be very close to 0, but whatever it is, right? So this one is a regression with 2 parameters. Okay, idea, that's a serious thing, okay, which is done really in practice. Instead of placing on the right-hand side of your regression just X, you start placing X squared, X cubed, X to the power 4, X to the power 5, okay, It's a polynomial. These things have a name, they're called splines. Some people actually, usually it's done as an alternative, but if the X allows you to, so there are restrictions on the values which X may take, okay? But some people take X, transform it in such a way that the restrictions are satisfied, and then on the right-hand side, they place the sign of X. the sine of the square of x, the sine of the cube of x, the cosine of x, the cosine of the square of x, the cosine of the cube of x, and so on, okay? These are like Fourier type models, they're called, but whatever. But there are people that do the game that I'm going to draw in blue for real. And what they do? Well, they use very flexible models, which are bored like the red one, but they can be twisted in special region of the space for x. Let me add a dot, some critical dot up here, okay, on purpose, right? One up here I added. They twist in special regions of the space for x the regression to track the data. So here, first of all, I want to fit this guy. Look at this guy. It's not well fitted. So let me start this way. And then I think I kind of want to remain below the red one, right? Because there is much more stuff below than above, right? So why to just go on the red? And here there is no, well, here we stay below, and then suddenly you got this patch of points, and you want to go towards them to kind of fit them, right? Because you get close to them, and the residual sum of squares benefits is minimized when you get close to the points. But then I've got this patch of points, 2 are below, 2 are above, so I go back towards the red here. And then there is this guy against this guy, so they basically tie, and so I go back. And then I want to fit these 2 points. And to do that, I want to stay a bit above my red line. Now, if you provide enough coefficients to the right-hand side of a regression, which is no longer a regression as you saw it, so we call it spline, you can have your model do the thing that you see here, which basically goes all over the place, trying to make as many dots happy as possible. All right, fantastic, right? Okay. So if you measure the R square of the blue model, easily it will be much bigger than the R square of the red model. And you feel happy. Problem. By chance, let's do that in square black. Life, 1 second after you're done doing this analysis, gives you this data point here. This one. Okay? So this is out of sample. Out of sample. Question, is that a crazy data point? No. Values of x below or above this point happen already. Values of y, they do not seem to be crazy in correspondence to this point because you're actually kind of close to the right regression. But the previous data that you had available were such that the blue spline was all twisted in this direction. Actually, it was because of this guy here. It was all twisted in this direction, drifting away from the red regression. What happens? Well, what happens now is that in correspondence to this new data point, you make a big, huge, massive error, and the error is this much, which you would avoid by just using the regression. Under the regression, the error would be actually small. So the regression would be okay with this point, but the blue thing is not. Lesson. If you use big models and you allow the models to actually fit every individual data point, what you end up obtaining is that the next case, the next observation will probably make you very unhappy. So models which are very rich, which are non-parsimonious, they tend to overfit. So blue is a case of overfitting, and as such, they tend to betray you when it comes down to forecasting. Oh, now I should close. Okay, but that's what I wanted to do. And okay, I'll see you tomorrow, and hopefully without problems. Guys at home, well, same for you here, of course. If you want to ask questions, I will stick around for a few minutes more, so I'm here. Ciao.